Okay, so today, let me lower this screen here. We are going to talk. I'm going to make that go all the way down to the floor. No, I'm not. This is boring. This part's no good. Skip ahead this part of the podcast. Okay. Right, so today we're going to talk about t-tests. We're going to talk about something you probably spend a month on in 21-26, so we're going to do it in about 55 minutes. Because you know how to do them already. Okay, now it's just the logic behind it, how they work. That said, don't be afraid to ask questions, obviously. I can't expect you to remember everything you learned from Dwayne. Right. God, it's slow. The transition seems slow to me. So, okay, you know this. Jumping right into the formula. Not much of a complicated formula. X minus mu over sigma. When you put something in terms of standard deviation units, which is what that is, we call it a z-squared. So to find the probability of a given value, remember we did that last time, right? How many people have an IQ between 95 and 107, or whatever the hell that thing was. If we want to find the probability of a value of a variable that's normally distributed, it's pretty easy. All we do is we turn it into a z-score, look it up in a table. Right? Or using the handy-dandy web tool that I showed you last time. Doesn't matter what, either of those work. It's not a very complicated thing to do, right? Z equals x minus mu over sigma, bang. Right? So it's no problem. You know this. This is stuff you've ran into before. This is probably the simplest thing. It is literally the simplest statistical thing you probably learned that's vaguely inferential in 21-26. That's where we start. But as interesting as this is, and it's not that interesting to most of you, I'm sure, we're usually dealing with means, not individual scores. It is incredibly rare when a research question is, how many people are above this? That doesn't work like that. That's not a research question. Research questions tend to be things like, do these two groups differ? You know, that kind of thing. So we're looking at group means typically. Are the means different from each other, right? That's what we care about. So we don't really care about individual values, but obviously it's going to come from the same place. We're going to do something with z that's going to allow us to compare means, right? So instead of knowing about the distribution of x, we actually typically care about the distribution of x bar. Remember the sampling distribution, all the possible values the statistic can take. The statistic in this case is x bar. So we look at the sampling distribution of x bar, and then we have something. So what we're trying to say now is how likely is it that we have a certain mean for a group? Right? It's funny teaching in a big room like this with a smaller group because when I'm walking around, then I stop and I look, and when it's a bigger group, I can look, and I'm looking at somebody. Sometimes I look and I go, and there's nobody there. And I'm talking to that chair right now. There's all techniques that we all have, but one of them is, you stop and you look at somebody and talk to them, and I do that all the time. I think you probably know that, except it's weird, because sometimes I'm talking to a chair like Clint Eastwood at the Republican convention in 2012. Anyway, we care about those. So there has to be a way that we can find the probability of a given mean, not just a given score. And of course there is, or we'd stop the course right now. So there must be, and there is. And that thing, as you probably know, is called the central limit theorem. It's going to allow us to do this. This is one of the few cases where I think you should memorize this. Now, in fact, I really do think you should memorize it, but you'll also have it written down in front of you. But I've memorized this. I've memorized this because it's the kind of thing that shows up on quizzes in 2 days. Literally in those exact words, in that exact order. Okay? Because the order of the words matters. It's a technical thing. Given a population with a mean mu and a variance of sigma squared, all that's saying is we have a population that has a mean and a variance, like any population. Okay? So that's all that says. It's just telling you that's what we're going to describe it as. The sampling distribution of the mean, we know what that is. That just says when we take a bunch of samples and we get their means and we plot the probabilities of those means. We'll have a mean of mu. Mu sub x bar equals mu. That is cool. That's telling us that the average of the sampling distribution of the mean will be the same as the average of the population. Notice that we don't have to know the average of the population. The average is like the sampling distribution of the means average will tell us it. We don't have to know anything to find something out. That's cool as hell. And a variance of sigma squared over n. It tells us the variance? How can you get that? That's wild. As it increases, this distribution will approach normal, no matter what the shape of the parent population distribution. I bolded part of that because that's pretty powerful. That's telling us no matter what the parent population distribution looks like, we're going to get a normal distribution for mu, mu sub x bar. So this is the sampling distribution of the mean. This is going to be true in all situations. This is going to be true even if you have a variable that only has two possible values. What's a variable that has two possible values? I don't know. How about flipping a coin? We call it heads as 1 and tails as 0, number of heads. And if I plot out the average number of heads you get, you will get a normal curve, even though it's zeros and ones. And I can just, let's do this as a little thought experiment. Okay? A little thought experiment. So, I have a marker here. Yeah. So if we got 10, we're going to flip a coin 10 times. How many heads should we normally get? What would you expect to get and not be surprised if you flipped a coin 10 times?
Like 6 out of 10?
6 would be a possible one, sure. And it can go from what, 0 up to 10, right? And 5 in the middle. So 6, sure, 6 is possible. What's another one? Guys, there's only 10 numbers. Okay, we could get 0 heads. Is that going to happen that often with a fair coin? It's going to happen, but it's going to happen very rarely. So rarely, in fact, yeah, it's hardly ever going to happen, probably really low. Same thing with 10. You ever expect to get 10 heads in a row? It can happen. By the way, 10 heads in a row is just as likely as heads, 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 tails, 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 heads, 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 tails. It doesn't matter if it's 10 heads or that. That's going to be pretty rare too. In fact, it's going to be just as rare as getting no heads. The most common thing, the common ones are going to be 4, 5, and 6. And in fact, nice job on 6, because that's going to be right up there. And 4, it's going to probably be right up there too. In fact, they should be equal, right? Because that's 4 heads, 6 tails, or 6 heads, 4 tails. The probability, that just intuitively, don't worry about math right now. That makes sense, right? Just on an intuitive level, that they should be the same. And it's probably the case that we would get, say, 3, that's 3, and 7, just about as often. So that's 3 heads and 7 tails, or 7 tails, 7 heads and 3 tails. I don't know, did I say the same thing twice? You know what I mean. They should be equal. Just, again, intuitively, don't worry about math. And I think 2 and 8 should be roughly about the same. 7, so this is 8. But lower. And then 1 and 9 should be low there. The most common one should be 5. I think we all see that. And look what we got. Like, you literally get a normal curve. Now that's just doing that on our own intuitive level. If you want to do this for yourself, feel free. If you've got a lot of free time in the next couple of days, get out a coin and flip it 10 times and do that 10 times and then see what happens. Or do it 100 times. Or with a die. You can do it with a die. You can do it with anything. You'll get a normal curve. You will always get one. It's cool. It's a property of the universe. The world just works like that. And you can see, I think, with our example, why it works like that. Right? No matter what the shape of the parent population distribution, the sampling distribution will be normal. It's crazy. It's cool as hell. Like, how many times in your life can you just guess things and know stuff on that level of precision? Not very many. It's pretty cool. Pretty cool. Okay, questions on that? Do you understand intuitively at least why this happens? I don't feel there's a proof. I think the proof isn't going to help anybody. Right? And I can't remember the proof, to be honest with you. But a mathematical proof isn't going to help anybody, right? But I think just thinking about this intuitively, I think it really does help. At least to me. population distribution doesn't matter. We had one with, with a head and a tail. It's a discrete distribution, and even then it works. What matters is random sampling. So when I say random sampling, I'm saying you're just flipping the coin randomly. That's all that means. But random sampling matters if we're sampling from some population, which we would be. But it doesn't matter as much as people think it does. It matters. The math assumes randomness. Okay? The math behind this, behind that thing, the central limit theorem, it assumes that we have a random sample. We hardly ever have random samples. When we're doing experiments with, say, intro psych students, do you think we randomly selected them? No, we hope they sign up. Right? Whatever. Stuff I've done with wild-caught birds, do you think I randomly sampled chickadees? No, it was the chickadees that came to the traps that I took from the wild. Right? It matters way less than we think. It matters, but hardly, not nearly as much as we think. So to find the probability of some mean, we just use our old friend, the z-score. So we're just going to use the z-score because we know the mean, we know the standard deviation. We're just going to sub that in, and we're golden. All right. Questions so far? Questions so far? You good? You good? A lot of writing. I like to see writing. It's good. Makes me happy. This is stuff that's better with writing, I think, than typing. Unless you're really good at the equations and stuff. I don't know. I just mean. Of course, we didn't have computers to take notes with. Well, computers existed. Not that old, but we didn't. You didn't have a computer you brought with you anywhere. Those existed. They were like $9,000, and they had a screen. I'm not kidding you, that big. It's like a suitcase. So no students had it, is what I'm saying. So that's what we're interested in, is the probability of x bar. We're going to use the Z formula. So here we go. So in general, what's happening? So you probably thought, and I know that you're taught, because I used to teach 2126, and I know he teaches it now, so I'm pretty sure he teaches it, that this is all the same formula. But a lot of times you have this idea that you learn all these formulas, and you really learn one, which is the Z formula, and everything else is a variation on a theme. And that's what's happening here. So for any z-score, it's x minus mu over sigma, but in our case, we're dealing with a mean. So we're going to go x bar minus mu, and then divided by sigma. Well, the sigma for the sampling distribution of the mean is sigma over square root of n. Okay. Now you might look at that and go, why is it sigma over square root of n? I think why it's mu, that makes sense. Well, maybe not why it's over square root of n, but let's think about this. And my running example keeps being what? We're going to randomly select 10 people from Algoma University and get their heights, right? So if we're going to get their heights, there actually is a standard deviation of the, I don't know, let's make up a number. Of the 3,500 people that go to school here, it's something like that. I don't know. They don't tell us things. That's not true. I just don't pay attention. Yeah, that's what it is. I don't pay attention. Mostly it's me not paying attention. Anyway, so let's say it's 3,500 people. We're going to sample 10 people. There really is a standard deviation and a distribution of heights at the school. Yeah. So if I sample 10 people, I get a certain standard deviation, right, of the mean. What would happen if I sampled 20 people? Would the standard deviation get smaller or bigger, do you think? The more people I sample, what will happen to the sampling distribution's standard deviation? What do you think? There's only two things. Well, there's three. Could you say the same?
It's small.
Yeah, it's going to get smaller. Yeah, it's going to get smaller, and it's going to keep getting smaller. In fact, what if I sampled all 3,500 students every single time? I'd get the same mean every single time, wouldn't I? And the variance I'd get then would be 0, right? Because the same thing over and over again is going to give me 0. So what this is saying is, look at this. As this thing here, as this quantity, as the n gets bigger, that thing gets smaller, right? So as, we're going to write this. That's cool. I didn't know I could do that. Okay. Maybe I did know. Anyway, sigma over the square root of n. Okay, I'm going to write a bit of a mathy thing on the board. And maybe you'll remember it from high school. Take the limit of that as n approaches infinity. Did anybody here learn limits in school? Tell me if you took calculus, you must have learned limits. All that says is what happens to that quantity as n gets monstrously large? What happens? It's going to get smaller. It has to. And in fact, once it gets to be infinite, that gets to be 0. Right? Because if we take a number, I don't care what the number is, it could be sigma, it could be 12, it could be chair. If you divide it by infinity, you get 0. Like the bigger you divide something by a huge number, you get 0. So what this is saying is, the bigger the population, as n approaches infinity, the smaller the variance. Okay? So the limit there might help some of you that have a bit of math background. If you don't, well, just think about it. What happens to that thing as n gets, monstrously large? It must get infinitesimally small. Right? Should tell you why we have more statistical power when we have more subjects. I'm sorry, participants. They changed it to participants in like 1992 or something, and it still pisses me off. Okay. It shouldn't. Things do. We've met, right? I hold grudges. So here's an example. This is the kind of example they make up in stats books. It's complete and utter bullshit. No one would ever do this, but here we go. So let's say we have 25 subjects or whatever are given an IQ improvement course. This would not help. You could be given a course though. You could, if you're given the answers, maybe that'd help you, but you can't really just take a course and make your IQ higher. Anyway, and the other IQs are tested after the course data with a mean IQ of 110. We expect them to have an IQ of 100, right? Because the population has a mean IQ of 100. Okay. And again, no one would ever do this experiment, but it's something, it's a nice example for a stats class because we know the standard deviation of the apparent population distribution of variance. Of IQ. As it says right here, IQ in the population has a mean of 100 and a standard deviation of 15. I mean, the tests are constructed this way. They're made to have that mean and standard deviation. Okay? All right. Okay? And so far, this is a good. Small group makes it a little easier, I think, for me to tell if people are lost. Now we do some pluses and takeaways. Okay. X minus mu over simply divided by square root of n. Sub it into the formula. Right. So we end up with 110 over 1 minus 100, that's 10, over 50 divided by 5, which is 10 over 3. Oh, it looks like, in fact, our IQ improvement course works. The probability of getting, because looking this up in a Z table, you say, Dave, the Z tables don't even go past 3. My calculator does. My calculator does. I still have the same calculator I got the first day I started graduate school. It does all kinds of neat statistical things. And it was bought for me by a guy who eventually was a professor at a university, and then he was asked to retire because of sexual harassment. But anyway, so I used to call him my friend. I don't anymore. A guy I knew. That's what I call him now. I still have that calculator. Anyway, what it'll do is I can put 3.33, and it'll give me the probability of that, which is 0.00043. It's pretty unlikely. Your Z table in a stats book never goes past 3. It just doesn't. Because 3 standard deviations from the mean is pretty far. Okay? So what this is telling us then, we can make a decision, we can reject the null hypothesis in this case, say that, yeah, turns out if you give people this IQ improvement course, their average IQ is higher than 100. Right? Now, of course, is it a random representative sample? All that matters. I don't care right now. I just did a little pluses and takeaways, did a little arithmetic, and there we go. This is stuff you've done. Right? Again, I know it's stuff you've done, and I know I'm clearly talking down to you as I say, well, then do the pluses and takeaways, so that'll make you feel silly if you say something. However, does anybody have any questions on this? I never do that. I do it every year, and I taught this course 29 times. There's 1 year in the last 30 years that I haven't taught this class because I was on sabbatical. Okay, good. Paul's teaching next year. You guys will watch, everybody drops the course right now. All of us take it next year. There's kind of an issue here, and the issue is that we don't typically know variances for populations, right? We don't typically know means for populations, but we can usually come up with something that's sensible, right? So you can say whatever, you can come up with some value. Like I could say the average height of an Algoma University student is 175 centimeters, and we can see if it's different. Fine. But what would the variance be? Can you come up with a variance? I don't know. How would I know that? It's a hard thing to know, except that the calculation I just did assumed we knew the standard deviation of the population, and we don't tend to know that. Well, the expected value of S squared is sigma squared, right? It's an unbiased estimator of sigma squared, isn't it? So the sample standard deviation is an unbiased estimator of the population variance, right? That's why, remember, we do divide by the n minus 1 to make it unbiased, right? Okay, well that's true, so why don't we can just sub S squared in for sigma squared. Well, that's kind of cool, actually. That's cool. The problem is now we actually have two sampling distributions to deal with. We have to worry about the mean, but also there's going to be a sampling distribution of the variance because it's going to change each sample. That's going to change depending upon n. That variance will be smaller. We just talked about this. That variance will be smaller the bigger n is. Right, and that's, again, just take a look up here. Instead of making this, it's the same kind of idea as this, because if we think about it with a sample standard deviation, I have a new knapsack, pretty excited by it. My old one, zipper broke. This one's nice. Nice new one. All right, think about this. We've got the variance equation. Let's put it here. I can't move that one. Oh, I can't. There's so many black whiteboards I can move. So think about sample standard deviation or variance. So sample variance. Again, look what happens. The n on the bottom, we have control over that. Make that big. The bigger that gets, the smaller the value gets. Okay. So the sampling distribution of this will change depending upon n. N's going to matter. So we can't use Z, because it's saying that things change if the number of subjects change. We can't have that. So we need something else. And you obviously know where this is going, considering the lecture's title is called t-tests. That's where we're going. There was a student years ago who worked with Paul, who we, around the department, we gave him the nickname t-test, because he was always just so keen and kept saying, is that a t-test? So we just called him t-test from now on. I can't even remember his name. No, actually I can't. I think. Right. So we'll use t. This is what t is. See, it looks very similar to the Z formula for the difference between a mean, a population mean, and a standard. In a sample mean. This is very similar. In fact, the only change is that's an S now, not a sigma. Well, it's the same formula. It's the same damn thing. And that's awesome. When you think about it, it really is easier to understand this stuff when you think it's all the same. It's really the same calculation over and over again. Okay, so let's keep going here. Now remember that t changes depending upon the number of observations. Because of this, see? Because we're using this quantity, well, the square root of that quantity. Because of that, because we're using the sample standard deviation, it changes depending upon the number of observations. So we're going to have to take that into account. Okay? We have to take that into account. And that is done through degrees of freedom, which we've talked about. We're going to look at the degrees of freedom to estimate sigma squared by calculating S squared. Okay? That's what we're going to do here. So T changes depending upon the values, the number of observations, sorry, and the degrees of freedom then to estimate sigma squared using by calculating S squared. That's what we're going to use. So the degrees of freedom are what's going to allow us to find a critical value to exceed and then find out if it's significant. Think about this though. You don't have to know anything about the population. Nothing. That's kind of cool, right? It almost seems like it shouldn't work. But the math behind it works. And I'm not going to get into the math behind it because it's not the point of the course. But it's cool that this actually works. Like, it's wild that we can estimate things about populations without knowing anything about populations. To me, it's kind of crazy. But that's how the universe works. Very cool. All right. So, what if we had pairs of observations? Because that formula, x bar minus mu, is for comparing a single sample mean to a theoretical population mean, right? So, like, for example, you know, the thing with, if we did it with IQ, we do it with IQ because we know the population standard deviation. We could do it with something else and see if it's different from some population value. Usually we're dealing with different groups, right? Like a couple of groups. So if we have pairs of observations, I'm just gonna do that. Okay. So if we have pairs of observations, sort of before and after, we can look at the difference between the observations. So if we have pairs of observations between, so it's all of us, let's say we're all going to get tested, and it's a, what kind of drug is it? What's it going to do? It's a blood pressure drug. We have to lower our blood pressure. Do we? I don't know. Mine's actually low. It's hard to believe, isn't it? You'd think mine would be incredibly high, wouldn't you? You'd think I'd be just this close to a heart attack constantly. My dad had a heart attack when he was 52. That's not what killed him. 12 more years for the brain cancer guy. But just saying. But mine, that's actually low. It's weird. I faint sometimes. So you would have seen that in class. Sometimes I go, okay, sec. And I have to sort of sit down. That's because I'm about to faint. Anyway, let's pretend we all have high blood pressure. And we have a new blood pressure drug we're going to try. So we measure all of our blood pressures before, and then we measure our blood pressure after we take the drug. Right? And we want to see if they're different. What would we if we took the difference of Dave after, Dave before, what do we expect to find if there is no effect of the drug? Dave after minus Dave before should equal what? 0, that's right. And it should be for all of us, shouldn't it? In fact, the average. And of course, it's going to be some fluctuation, so it'll be a little bit above, a little below, but on average, if there's no effect, it should be 0. If the drug works, it should be non-zero. Right? That's okay. So we understand the logic of this. So with pairs of observations, we can look at, that's why it says x bar sub d. That's the average difference. Okay? The average difference. Again, it's the same formula. And you're looking at that, you're saying, no, it's not the same formula, Dave. Why doesn't it say minus mu? It does. You know what the minus is? Minus 0. We expect there to be no difference. So it will be x bar sub d minus 0. So we just take the minus 0 off, because why should we leave that there? But that's there. It's like, you know, it's understood to be there. So it's the same formula. Okay? It's the same formula again. So we take just differences between the two before and after. Right? So pairs of observations, the ultimate example is before and after, and that's usually where you'd use this. But you can do it with matching. So we could, let's say we're doing the blood pressure experiment, but we want to have two groups, different people. And what we do is we match people up. So we take all of our blood pressures before, and we match people up. So it turns out that Madison and I have exactly the same blood pressure. Seems incredibly unlikely. I'm a 60-year-old man. However, yeah, well, for both of us, really. Both of us, really, just me. You. I'd be fine. You're like a third my age. But anyway. So if that's the case, we can give, say, me the drug, and then we can compare my score to her score. We just subtract her from me, because we've matched the two of us together. Now remember, if we've matched the two of us together, we're the same on one thing. Heart rate. We're different on everything else. We better be damned sure it's only heart rate we care about, and it is in this case. That's why I'm using this example. It's a physiological measurement. This isn't some sort of fuzzy thing. This is something we would measure with a blood pressure cuff. It's pretty, what's the word I'm looking for? Precise. So be careful. Subjects are different now, as I just said, on everything else than what you've matched them on. So we tend to use this in things like drug studies, things like that. You'll use it in a drug study or something that's going to affect a physiological measurement that is reliably measured and accurately measured. Okay. So you don't see this that often, but you will see it. I've used these before and after. Sure. I've had a lot of students use these in their honors thesis projects as well. Again, because it's a pretty reasonable. It's not a hard bit of math to do, right? And it's not a hard bit of design either. Just make sure that if we're doing before and after, no big deal, right? And the standard deviation of the difference. That's why it's S sub D divided by square root of n. Okay? Again, still the same formula. Okay. Questions so far? Okay. Oh, yes, good. Okay.
I'm being honest, I'm a little lost.
Okay, what are you lost on?
So you're saying the X bar D is the average difference. So
Yep.
it's the same, it's essentially, so it's the same score as the T-score still.
Yeah, it's still a t-test.
It's still the T-test.
It's still a t-test.
Because that's where I get confused. Where I'm like, the letters that change, and then if it's the same thing, and then I'm like, oh, if I've done it
Okay,
wrong.
this is what I'm trying to say is that it's all the same damn test. These
Okay.
are all t-tests, right? So when you're comparing two groups like this, this is a special case of two groups. We'll do a more general case in just a moment, as I'm sure you can tell. But the special case, when you do this, you might say, well, then why do we ever use the special case? This has a lot more statistical power than the thing we're going to talk about next, except it only works in your very specific circumstances, like using someone as their own control or matching subjects. So you don't see it a lot out there because it's only good in certain situations. If you had, for example, and you'll see a lot of animal stuff where you can have developmental things, and you can have two rats that are littermates. That's a great control. Like they're basically the same animal, or twins. Twins, you could do this with twins. That'd be fun, right? But typically, it's before and after the same people, or some measure, like I said, that is the only thing that's going to be affected by matching like this. So something like blood pressure or something like that. So in that case, we'll use it. I shouldn't say it's rare. Like I said, I've used it in my career, but it's not something that you. It's not a general thing.
Okay.
Right? Does that make sense?
Yes, yeah.
Okay, good.
It's the same thing, but it's a very specific
Yes,
circumstance.
and they're
use.
all the same things, and they're all used in specific circumstances. We're getting more and more general as we go along here. And probably more and more useful as well. Very rarely are we comparing single group means to a theoretical population. I've done it, but it doesn't happen that often. I've also been doing this more or less for 40 years, so you're going to do most of the tests at some point, but not very often do I do this. No. Other questions? Thank you for just saying so. God, see, it took no time to explain it, right? Okay. What if your pairs aren't matched? This is our general case. This is the one that we're all used to. We might want to call this the independent sample t-test or the uncorrelated t-test. You'll hear that sometimes. This is the problem. They all have these different names. They're just t-tests. They're all the same formula. They really actually are. So maybe you have two populations. At least that's what you're trying to find out. You have two populations around. So the hypotheses here are as follows. So our HO is that mu1 equals mu2. mu2, of course, my favorite band. I do that. I have to do it now. I've been doing it for all these years, so I just can't help it. So I just do it. I know it's fun. So our hypothesis, if they're equal, we would say that u1 equals mu2. The two groups are the same. We have two groups here. This isn't two matched pair groups or anything like that. This is just two groups. So we've got we have 12 people in here. So 6, 1, 2, 3, 4, 5, 6. And then the rest of them, we're cool people, they suck. But that's our two groups, 6 and 6, okay? So in that kind of case, we haven't matched our groups in any way. We could do the blood pressure thing. Probably wouldn't, because it's better to do it before and after. So we'll do some other experiment, whatever the hell it is. I don't know. How far can you throw a ball? We can throw a ball farther than you. Can we? You guys got a good arm? And we're going to test that. So we would assume that the two groups are the same. In fact, probably a pretty good guess that there isn't much of a difference between how far the two groups of 6 could throw a baseball. It's probably about the same. Our HA is that mu1 is not equal to mu2. Ho and ha. Ha 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 ha. Ha 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 ha. It's an old song. Laughing. Ha, ha, ha. Good. Well, the original T formula looks like that, remember? Which actually comes out of the Z formula. Again, it's all the same formula. It's our original formula. So the original formula says that's the statistic we're interested in, right? That's the HO. Because for a one sample t-test, just what mu, you're just saying that mu sub 0 equals or equals 100 or is greater than 100 or something like that for the IQ example, for example. So that's our HO goes here. So it's statistic minus HO divided by error. Error is just, some measure of spread, and it's okay. So really, it's T equals statistic minus HO divided by error. So that's what T is. T is statistic minus HO divided by error. It's kind of great. The t-test was developed by a guy named Gossett, who was worked at Guinness Brewing in Dublin, Ireland. He worked at Guinness Brewing. And when he first published this, Guinness didn't want him publishing under his own name because they thought that another brewery would scoop him up because this is a pretty powerful thing. This is for quality control. That's why he developed this thing. So he published the name Student. He said he published as the name A Student. So you'll hear it called Student's T-Test sometimes. And the guy's name wasn't Student. It was Gossett. Remember his name? He had the coolest job ever. He was a statistician at a brewery. That's like my dream job. Just do stats all day and get hammered. Awesome. If they had video games in there, throw that in there. It'd be great. Maybe watch Mad Men every so often. So that's what we have. Statistic minus HO divided by error. So let's build the formula. So the statistic we're interested in are the two groups different, x1 bar 1 minus x bar 2. So that's we6 and u6. Are we different from you guys? So we would do that. We would subtract our mean from their mean or whatever. And our null, or our hypothesis, is that mu1 minus mu2 equals 0. That they are the same. Because if they're the same, mu1 minus mu2 must equal 0. Right? Everybody following this so far? It's good. Yeah? You're good? Okay, this is good. It's boring, but it's good. And we're going to divide by error. We'll figure out the error in a second. So again, practically, just like with the one sample t-test that had technically says minus 0 at the... Well, that should be minus 0, so screw that. We'll remove that. It just makes the formula easier to write out. That's why, again, this looks like a different formula. It comes from exactly the same place. So now we just have to figure out what the error is. Well, our variances are going to have to be weighted somehow. Variances depend on the number of subjects. Right? They divide by n. Well, if they divide by n, let's do that ourselves to weight them. And you might think, well, we have two things. We get x bar 1 minus x bar 2. Do we do s squared 1 minus s squared 2? No, you add them. Okay? So if we're going to work this out, we should have s squared sub 1 over n1, s squared sub 2 over n2. So our formula is that. And you'll see now, you go, oh, that's the t formula. So this is where this comes from. Again, oh, did I make a mistake there? Oh no, they both go 1, 2, 1, 2, good. Yeah. Oh no, let's say 1. Yeah, that's right, that's right. Okay, I was afraid it was a typo there. I think there used to be one there a long time ago, and I keep thinking it's going to be there. So, again, you can see that something that looks like a different formula. This looks like some brand new thing, and you have to, I'm going to memorize another formula. Well, first of all, you don't. You can bring your stuff to the tests, right? But also, it's the same formula. My voice is getting higher and higher. I don't know what's going on there. Soon only dogs will hear it. Garage doors in the neighborhood will start opening. People's TV channels will change. So really, we have the same formula. It's the same one again. We just sub different values in for the statistic, for the HO, and for the error. Now, if you look at that, you can see that it's weighted by n, but an assumption is made here that I didn't tell you about yet, and that assumption is that these two variances of these two groups are actually equal. They're not going to be equal, of course, but the math assumes they're equal. The math behind it is assuming they're equal. They're never going to be equal. You might say, well, Dave, how unequal is 2 unequal? Yeah, if one's 4 times bigger than the other. That's kind of a rule of thumb. What happens when they're not equal, the variances for the two groups? Because again, these are all group statistics, right? So if the variances for group 1 and group 2 are off by, more than, like I said, about 4 times, it makes the test more conservative. So you're not going to make any false positives, but you're going to get false negatives. So while you're not going to make a fool of yourself and say that, I don't know, that there are aliens that are here living among us with their ESP powers. I'm going to say that, you better have some pretty good evidence. You're not going to make an idiot of yourself like that, but you're going to miss something perhaps that was there. It's like, oh, that was a thing I could have discovered, but somebody else did because, damn, statistical power. So if the variances aren't equal, things do change. So if you look at your numbers, like just as a rough calculation, go, this is 4 times bigger than another one, maybe we should do this differently. Or if you did exploratory data analysis, and you look at a graph, a nice little bar graph of 2 groups, and you say, this bar graph says that shows the 2 groups are different, yet my t-test doesn't come out as a significant difference. What the hell's going on? Well, it might be your variances are different. So what we want to do is get this quantity called pooled variance, s squared sub p. And again, it's just a weighted average of the 2 variances, and then we use that, as you can see in the formula up there. Okay. Sure, I've got all the subscripts. Yes, I do. Good. Yeah, they're all right. They may be wrong in the notes. They're right there. Let's double check that they're right. Okay. Because it should be, it should be n sub 1 minus 1 times s squared sub 1 plus n sub 2 minus 1 times s squared sub 2 divided by n1 plus n2 minus 2. Okay. So again, things just change a little bit, but it's the same, again, it's still the same formula. How many degrees of freedom does this have? When you look this up in a t-table, which is what you do, or when SPSS does it for you, or SPSBT, when it looks it up, how many degrees of freedom is this going to have? And it's general, obviously. There's no real numbers here. They're just n's and stuff. But how many degrees of freedom? Well, let's do it backwards. How many things did we fix? Well, we calculated 2 variances. So we fixed 2 different means. So it's n1, that's the number of subjects in group 1, plus n2, that's the number of group 2, plus or minus 2. We lost 2 degrees of freedom because we fixed 2 variances. Okay? Make sense? You'll see sometimes if you and I encourage you when you start, this is the time to start playing with software. If you have not yet downloaded PSPP or used SPSS in the one of the school computers, or you've got another way to have it that I'm not aware of, I can't encourage that. I can't. And I don't. But if you do, it's simply the time to start playing with it. And you'll see sometimes you'll get a thing and you'll say the degrees of freedom, and it'll give you weird numbers like 17.3. It's like, excuse me? That's an entirely different way of doing it. And you don't usually see partial degrees of freedom. It's not something that typically shows up, okay? Okay. So this is going to have some assumptions. When I say this, t-tests have assumptions. People often ask, why are these assumptions there? Well, the math behind this, certain assumptions had to be made when Gossett figured out the t-distribution. He said, well, we're going to assume this is like this and assume it's like that, because then you can do the math behind it, right? So the first one is a simple random sample. So a simple random sample is literally all of the possible experimental units, as they are technically called in statistics. So all the possible participants, subjects, experimental units, whatever you say, have an equal likelihood of being chosen. I'm going to ask you practically, how often do you think we literally have an equal number, an actual real simple random sample in psychology? Because I think it's never. It's almost certainly never. Right? So there's no way we ever have random samples. The math assumes we have random samples, but we never have random samples. That's not that big a deal. It's a big deal for generalizing to the population. So for looking, we want a representative sample to generalize the population, but that's not what this is about. This is about our differences, our group differences, real. That's all this is saying, and you can violate the hell out of this. We do it all the time. How often do you think honors thesis projects literally have an equal probability of everybody in the world being in them? Well, no, obviously. It's the people who are in intro psych. And that's everywhere, not just here. We never have single random samples. And it's not a big deal. It's not a big deal, again, for the statistics themselves. This one is, however, independence of observations. So if I know a score, somebody's score, that doesn't help me understand anybody else's score. Every observation is independent. Okay? I like to think of this as the no cheating one. Right? So if I know Arwen's score, that doesn't help me understand Madison's score. I don't think you're cheating off Arwen, Madison. Please don't take that way. I think Arwen's cheating off of you. But it's a joke. These are jokes. But seriously, I think of it that way because if I know your score, I don't know your score. Right? Your score, it doesn't matter who you're sitting beside. It doesn't matter where you are in a classroom, that kind of thing. It shouldn't. Okay? And think about it. Do any of the things we calculate, like averages or variances, do any of them ever mention, except if you're the third one or something? Or if you were beside somebody else, that whole thing? No, they don't say that. They just say, here's a bunch of numbers. Right? And the bunch of numbers are just a bunch of numbers. Remember, numbers don't know where they come from. It's an important thing to think of. The numbers don't know where they come from. So you could do these calculations, when you violate these assumptions, they don't work properly. But you get numbers, like it all works, it just is wrong. Right? So independence of observations is huge. You must have independence of observations, or the whole thing collapses. So it's another probability statistics kind of basic thing, is the idea of independence. And the math for probabilities of independent events is different than probabilities of dependent events. And we assume independent events, and then we go backwards. And that's what, of course, Gossett did. He assumed independent events. So we have to have independent observations here. And homogeneity of variance. That means the variances are the same. Now, they're never the same. We can violate this to a point. We can violate it up to about one being about 4 times bigger than the other one. Once they're not if it's more than 4 times bigger, it gets hard. You use the pooled variance, still you're violating an assumption. So we need our variances to be the same. Think about this. Sometimes you'll get 2 groups. Just draw here. Just draw a little. Here's a. Okay. So there's the error bars. So if you look here, these error bars overlap. In that case, you're not going to find a difference between the groups, but you might think that there is a difference. There is. One's way bigger than the other one, but there's so much variance. Well, maybe if we did maybe there's something we can do to the numbers to fix them. And we'll talk about that. That's coming. But it's often an indication that maybe some assumption is violated or something if you get this kind of overlap, even though there's a difference. Okay. Questions about t-tests. In a sec, we'll go off this. I'll show you some stuff, SPSS stuff. But thought we'd finish this part up first. Okay. All right. So I'll stop that and we'll fire up SPSS. We'll take a look at it here.